So we talked about the parameterizations, and we looked at it for different surfaces in R3, and it's a way to move around the surface. Now, how are we going to get the area of this small patch ds? Okay, here is the formula for it. Okay, you'll take the partial derivative of r with respect to u, and that will give you a tangent vector that points along this way. Okay, that would be the partial derivative of r with respect to u. And you could also take the partial derivative with respect to v, and it'll be a tangent vector this way. Okay, that would be the partial derivative of r with respect to v. These are tangent vectors. Now sometimes you'll see this written as tv. Not to be confused with taking a partial derivative of some vector t. No. This in pink is the same as what I'm highlighting there, and sometimes you'll see this written as tu as a vector. Okay, and these are tangent vectors. They run along. You could think about them as sort of a velocity vector if you hold the other variable fixed. Okay, so if you hold v fixed and you take a partial derivative with respect to u, then you're getting that blue vector, and it's like sort of like a velocity with respect to u. And the in pink, if you hold u fixed and you vary v, you could think about the pink vector as sort of a velocity vector when you hold with respect to v, right? Holding u fixed. Now, why would that formula work that we saw for the getting the surface area of a small patch, as we see up here? This delta S of that small patch is equal to the cross product of tu, which again is partial r, partial u, and tv, which is partial r, partial v, the partial derivatives of the parameterizations. Well, if you have the velocity, right, tu, velocity in air quotes there, and you multiply it by delta u, you're going to get that small displacement. It's going to give you the length, actually, of the distance or change in position that you've traveled if you hold v fixed and vary u, and likewise for tv delta v. So you'll get vectors that actually give you the length of that green patch over there. Now you cross these together, and what do you get? That's the area of the parallelogram. We looked at that when we talked about the cross product. So the magnitude of that, the magnitude of the cross product of tu cross tv, is the area of that parallelogram. And as you take the limit as delta u and delta v goes to 0, you get the exact area of an incredibly small patch. Okay. And just a quick remark, notice that tu cross tv, since both tu and tv are tangent to the curve, the cross product will be normal to the surface. Okay, since tu and tv are tangent to the surface, their cross product will be normal to the surface. Okay, so we're ready now then to get our formula, since we got the surface area of a small patch. And here is the formula that we're interested in. Okay, this is the formula for surface integrals of scalar functions. You take your parameterization. That's why the parameterization is the only creative step in this. It's the only one that takes some ingenuity. After you get the parameterization, you just run it through that formula. So you plug the parameterization into your function of 3 variables, and you'll get your ds vector, also in this light blue, by taking the partial derivatives of the parameterizations, crossing them together, then taking the magnitudes. Okay, and here you get your bounds from your parameterizations. Quick note: if this function f was 1, well, then you could treat this whole thing as 1, right? And you get a double integral of ds. What do you end up with when you do that? You end up with the surface area. And that's why the surface integrals of scalar functions are often used to compute surface areas of arbitrary surfaces in 3 dimensions. Okay, you would here take this function of 3 variables and just set it equal to 1, and that will allow you to compute surface areas.